All right, so in this video, we are going to solve problems related to entropy, enthalpy, and free energy. So let's look at the problems. So the first problems will ask you to predict the sign of delta S, that is the change in entropy of a substance. So for these ones, what you are looking for is, are we forming more of a gas or less of a gas? Are we forming more of a solution or less of a solution? What you are looking for is, are we increasing disorderliness or are we increasing orderliness? So let's look at the problems. Problem A. So predict the sign of delta S for each of the processes, starting with A. If you look at A, we are moving from gas to liquid. So here we are increasing orderliness because liquid is more ordered than gas. So in this case, the entropy decreases. So this implies that entropy decreases, which means the sign here is negative. So since the entropy is decreasing, the size is negative. So for B, solid carbon dioxide sublimes. So sublimation is formation of gas from solid phase. So in this case, we are increasing disorderliness. So here we are getting more disordered, which implies that entropy increases. Therefore, the sign here is positive. So if I ask, give me the sign in the change of entropy for solid making gas. In that case, we are making a more disordered substance because gas is more disordered than solid. In that case, the entropy will increase and the sign will be positive. What about C? So we have that reaction equation. For this one, we say more gases are formed. So here more gases are formed, therefore entropy increases. Entropy increases, which means sign is positive. You can see that this side we have 2 gas molecules, this side we have 3 gas molecules because there is 1 here. So we are forming more gases, therefore more disorderliness. That implies that entropy increases. For D, we have same number of gas molecules on both sides. So this implies that no change in entropy. So here the entropy change is 0. So what we are saying is, for this case, delta S is equal to 0. What are we saying? Here we have two gas molecules. One gas molecule is here, and the next gas molecule is here. So we have two gas molecules on the reactant side, and then we also have two gas molecules on the product side. So we are not increasing or decreasing the gases. As such, the change in entropy is 0, or the entropy is constant. What about E? E, we are moving from solid phase to solution phase, which means we are more disordered. So any increase in disorderliness will mean an increase in entropy, which implies delta S is greater than 0, or the sign is positive. So we can say that for this one, the sign that we want is here. We have negative sign, positive sign, also positive sign here, no change here, and positive sign for this problem. Let's move on to the next problem. Let us consider the situation, the combustion of propane to make carbon dioxide and water. So it says, calculate the entropy change in the surroundings when this reaction occurs at 25 degrees Celsius. So that is question A. So as a reminder, change in entropy of the surroundings is equal to negative change in enthalpy of the system divided by temperature. So in this case, we have delta H reaction, which is also the same as system. Delta H reaction is negative 2044 kilojoules. Please change this one. Always change it to joules. So the joules will be 2044,000 joules. You don't want to put this one in this equation in its kilojoules form. You want to use joules. So for this one, I'll go on and say negative. Then inside I'll put negative 2044,000 joules divided by the temperature. This temperature must always be changed to Kelvin. So this is 298 Kelvin. So I'll say here divided by 298 K. And for this one, the answer is 6859. So the units are joules per Kelvin. So that is the change in entropy of the surrounding. So we need to remember this formula. Delta H surrounding is equal to delta H system divided by T. The second part, determine the sign of the entropy change for the system. Now for this part, for this B, you are going to look at the equation as it is given there and count the number of gas molecules on both sides. So let's count the number of gas molecules. We have we have 6 gas molecules on the product side. Actually, 6 gas molecules on the reactant side. So we have 6 gases here. On this side, 4, 7. And we have 7 gases on this side. So since we have more gas molecules on the product side, then the entropy increases. So we say since we have more gas molecules on the product's side, the entropy increases. In this case, the delta S of the system is greater than 0, and this implies the sign is positive. So we determine the sign of the entropy when given a chemical reaction by counting the number of gas molecules on the reactant side and the number of gas molecules on the product side. C. Determine the sign of the entropy change of the universe. So we know that delta S universe is given by delta S system plus delta S surrounding. But we know that both delta S surrounding and delta S system are positive. Both surrounding and system are positive. Right. So if you add positives, it gives you a positive. This implies that the delta S of universe is also positive. Or we can say that delta S universe is greater than 0. So we are answering the question, determine the sign of the entropy change of the universe. We found that the entropy change of the universe in this case is greater than 0. So the last question is the reaction spontaneous? So we are answering this question. Is the reaction spontaneous? What do we know? For a spontaneous reaction, delta S universe must be greater than 0. So we say for a spontaneous reaction, delta S universe is greater than 0, which implies this reaction is spontaneous. So the reaction we are dealing with is spontaneous because the entropy change is greater than 0. So let's Let's look at another problem. So this is a different problem. If you remember in first year you did Hess law. Now you used Hess law to calculate enthalpy. But now we are using the same Hess law, but now we are calculating entropy of the system using Hess law. The question is, calculate the entropy change of the overall reaction below, given two reactions, reaction 1 and reaction 2. So this is our overall chemical reaction. So how do we solve this problem? To solve this problem, we look at our overall chemical reaction and see how it is similar to the two reactions given below. So how do we do that? First we are going to select carbon monoxide here. We are going to select carbon monoxide and look at the two equations given below and see where carbon monoxide is. Oh, we have found carbon monoxide. So we have carbon monoxide here from this reaction. The second part is we need to count the number of carbon monoxide present in the overall chemical equation and in equation 1. So the overall chemical equation has 2 carbon monoxide as indicated here. Now our reaction in equation 1 also has 2 carbon monoxide. That's the second part. The third part is we are going to look at the carbon monoxide and say, in the overall chemical reaction, is carbon monoxide a reactant? What about in equation 1? Is carbon monoxide a reactant? So we find that in both overall equation and equation 1, carbon monoxide is reactant. So three things. We have 2 carbon monoxide in our overall equation. We have 2 carbon monoxide in our equation 1. So we are not going to change the number of carbon monoxide in equation 1. 2. Carbon monoxide is a reactant in the overall chemical equation. Carbon monoxide is a reactant in equation 1. So we are not going to do anything. We are not going to reverse equation 1. So what we are going to say is equation 1, we leave it as it is. Leave equation as it is. Because whatever we are given about carbon monoxide in the overall equation is the same for carbon monoxide in equation 1. Now, what else do we look at? For equation 2, we are going to look at nitrogen. And we are going to ask the same questions. The first question is, how many nitrogen atoms do we have in the overall chemical equation? We see that we have 1 nitrogen atom here in the overall chemical equation. Also, we have 1 nitrogen molecule here in equation 2. So we are not going to change the number of nitrogen atoms in equation 2. Another question is, what is nitrogen in the overall chemical equation? We see that in the overall chemical equation, nitrogen is a product. So nitrogen in the overall chemical equation is a product. Here, nitrogen is a reactant, and we don't want that to happen. So for equation 2 to be like the overall chemical equation, you have to reverse the whole equation. We have to make nitrogen molecule here, we have to make it a product, not reactant anymore. So what I'll do is I will say reverse equation 2. Equation 1, we leave it as it is. Equation 2, we reverse it. So when we do that, we are going to have 2 carbon monoxide, oxygen to give us 2 carbon dioxide gas, and the change in entropy, I'll just say delta S, will be given as 173.4 joules per Kelvin. So this one, we leave it as it is. But we are saying we are going to reverse equation 2. So when you reverse equation 2, you also need to reverse the sign here. So we are going to have 2NO for equation 2, which is a gas, to give us N2, which is a gas, plus O2, which is a gas. And also we reversed this. So the positive will become negative 24.5 joules per Kelvin. When you reverse the equation, you also reverse the sign of the equation. Now, when you add the 2 equations, they should give you the parent equation. How do we know that? We know that we are going to get the parent equation because oxygen here will cancel with this oxygen because they are on opposite side. Oxygen in the reactant side will cancel with the oxygen in the product side, and we are going to remain with 2 CO gas plus, so we add all the reactants to give us, we also add all the remaining products. So the equation we have here is the same as this parent chemical equation. How do we get the change in entropy? We just add the 2 here. So you add the 2 entropies and you are going to get minus 197.9 joules per Kelvin. So what we are saying is this overall chemical reaction, the change in entropy for this chemical reaction is equal to minus 197.9 joules per Kelvin. So in this case, we have used Hess law to determine the change in entropy of an overall chemical reaction using several steps or using several reactions. In this case, we have used 2 chemical reactions. All right, so to cement this understanding about Hess law and entropy, let us solve another problem. Calculate the entropy change of the overall reaction below, given reactions 1 and 2. So this is our overall chemical equation. And we have our reactions here, reactions 1 and 2. So as usual, how do you approach this problem? As usual, the first thing is to study the overall chemical reaction and look at the species present in the overall chemical reaction. Now, here we have 1S. We have 1S here, which is a reactant. But here we have 2S, which are also reactants. We have 1 here. We also need to have 1S here. So how do you obtain 1S? You obtain 1S by dividing, or by multiplying this equation by half, because half is going to reduce this 2 to 1. So you multiply this equation by half. By that I mean you need to multiply the whole equation. So in the end, you are going to have S solid plus 3/2 oxygen, which is gas, to give us SO3 gas. Now, if you are multiplying by half, you are also multiplying this one by half. So the change in entropy in this case is going to be so let me just look at the numbers. So the change in entropy, you have to divide this one by 2 or multiply it by half. Divide this one by 2 or multiply it by half. So the change in entropy will be minus 83.1 joule per Kelvin. So you are done with equation 1. Now what else do you look at? The second thing you look at, for now, ignore the oxygen, because we have oxygen on both equations here. We have oxygen here, oxygen here. So for now, ignore the oxygen. Look for this, SO2. Here we have 1 SO2, here we have 2 SO2. So it tells us immediately that we need to multiply this one also by half, so that we have 1 SO2 in both cases. But here, the SO2 is a product. So this is a product. This one is a reactant. So in that case, you need to reverse this equation. So you are doing two things. The first thing, you multiply it by half. The second thing, you reverse it, so that the SO2 is a product in the overall reaction and in reaction 2. So what I'm going to have is SO3 gas to give me 2SO. Not 2. I'll just get rid of the whole thing here. So to give me, because we have divided by 2, so to give me SO2 gas plus half O2. Because we have multiplied by half, so the oxygen also must be half. Now, since we have reversed, this one will become positive. This one will become positive because we have reversed. The negative changes to positive. But also because we have multiplied by half, we need to divide 188 by 2. So we are going to have plus 94.0 joules per Kelvin. Now, when we add the two reactions, I mean 3.5 minus half, if we look at this oxygen, 3.5 minus half, this oxygen cancels and there will only be one oxygen here. So that's what's going to happen to oxygen. Also, SO3 cancels with this SO3 because this SO3 is a reactant, this SO3 is a product. So they are going to cancel each other. What we are doing is we are remaining with S on the reactant side and the oxygen, one oxygen present here, which is a gas, then to give us SO2, which is also a gas. So this is similar. This equation is similar to the parent or to the overall chemical equation here. The entropy, you just add the two entropies. So you add them and they give you plus 10.9 joules per Kelvin. So what we are saying is the change in entropy of this reaction is plus 10.9 joules per Kelvin. Let's move on to our next problem. So in this problem, what we want to use is an equation that we have already seen. An equation that says delta G is equal to delta H minus T delta S. That's what equation we are going to use, because here you can see that you are given delta H, here you are given delta S, and you are given temperature here. So let us consider this equation as given there. A, calculate delta G at 25 degrees Celsius and determine whether the reaction is spontaneous. B, if the reaction is not spontaneous at 25 degrees Celsius, determine at what temperature, if any, the reaction becomes spontaneous. To solve this problem, first of all, you need to change the temperature from degrees Celsius to Kelvin. So 25 degrees Celsius is 298 Kelvin. These problems always use Kelvin. Reason is, you see here, our entropy is given as joules per Kelvin. So you cannot use degrees Celsius for that. So let's solve equation, or let's solve problem 1. Calculate delta G at 25 degrees Celsius. So for our solution for A, we are going to say delta G is equal to delta H minus T delta S. So delta H must be given, must always be given in joules. So delta H must be given in joules per mole in this case. So if you are given kilojoules, you have to change kilojoules to joules. So what we are saying is 95.7 kilojoules is equal to 95700 joules. That's what you are going to use. So here we are told delta H is 95700 joules. So I'll say per mole. Or maybe I'll get rid of per mole because I don't want it to give us trouble. So we have 95700 joule. Now this one minus our temperature is 298 Kelvin. This one times delta S. Delta S is given as 142.2 joules per Kelvin. So we'll see that the Kelvin here will cancel, and we are just going to have joules in both cases. When you add the two, you get 53,324 joules. So most of the time you want to report your delta G in terms of kilojoules. So the delta G of this reaction is 53.3 kilojoules. Now the question is the reaction spontaneous? That's what the question is. But how we answer this question, a spontaneous reaction must have negative delta G. So we say delta G for a spontaneous reaction is always less than 0, or we can say negative. But in our case, we have a positive delta G. So this one is a positive delta G. So in our case, we have a positive delta G. This implies the reaction is non-spontaneous. So the reaction is non-spontaneous. Now, another question is, if the reaction is not spontaneous at 25 degrees Celsius, determine at what temperature, if any, the reaction becomes spontaneous. So that is B. So to solve B, we know that the reaction is spontaneous only when delta G is less than 0. But for delta G to become less than 0, it needs to pass through 0. So it needs to pass through equilibrium first before becoming spontaneous. So what we do is we put, instead of delta G, we put 0. So 0 is equal to delta H minus T delta S. So that is an equilibrium situation. So at that point, we are going to say that is delta G. Oh, why am I saying delta G? Let me make a change here. this one must be delta H. So we say 0, which is delta G, because we know that at equilibrium delta G is equal to 0. So we say 0 is equal to delta H, which is this one, minus T delta S, which is this one. So what we are saying is delta H is equal to T delta S, or we can say that T is equal to delta H divided by delta S. So in our case, the temperature we are looking for will be given by delta H, which is 95700 joules. Remember, always use joules instead of kilojoules. Divide by delta S, which is 142.2 joules per Kelvin. And for this, we see that here the joules are going to cancel, and we are going to remain with Kelvin as our unit. So we are going to have 673 K. So what we are saying is the reaction becomes spontaneous at temperatures greater than. So the reaction becomes spontaneous at temperatures T greater than 673 Kelvin. So the issue is, if you put 673 Kelvin here, if you put greater than 673, or let's say if you put 690 Kelvin here, the whole thing, the delta G, will become negative. That's what it means. So if you put a temperature that is greater than 673 Kelvin, the delta G is going to become negative, because the negative part of the equation here, this negative part of the equation, will get bigger than the delta H, than the positive side, and then the whole equation will have a negative sign. So we need to know how to solve these types of equations, especially these types of questions. So check for the next video to continue on these problems. Thank you.